We will begin our presentation with the research objectives and methodology, and then dive into the results of the mapping of non-natural gas power facilities and power connections. We will also cover logistical considerations, engineering design, financial analysis, and we will wrap up with the final recommendations. So for the next slide, we have the objectives. So the engineering work stream had three objectives. The first one is to map the existing infrastructure of facilities not yet using natural gas. Second is to determine the logistics for delivering the LNG to these zones, to the ecozones in Batangas. And third is to assess the feasibility of small-scale LNG-based power and thermal systems. For the next slide, please, and then another slide. We have the methodology. So for the first part, a survey has been conducted, so earlier presented by Dr. Carl and Doc. So this is together with the Ecozone Economics team to identify the facilities in industrial areas in Batangas that currently use fuel sources other than natural gas, and then including the power sources for their operation. The second part, which is the logistical requirements for the natural gas supply. This involves desk research on the relevant standards and considerations in the transport of LNG from the import terminal to identify storage and regasification facility in an SEZ. And the third one is on the techno-economic analysis. So the results of the demand survey feeds into this analysis where the technical aspect was simulated in Aspen HYSYS, and the financial feasibility is evaluated using the NPV and IRR criteria. So for the results, for the next slide, another one. Yeah, so for the first one, our data were drawn from the 35 survey locator firms, as also earlier discussed, and engaged with stakeholders through focus group discussions. And aside from that, we also reviewed technical literatures, international guidelines, and prior GPDP researches. Next slide, please. Okay, so this is for the first objective. The figure here highlights that SEZs with dense concentration of energy-intensive equipment. So earlier it was more on the demand. This time it's more on the concentration of the facilities in SEZs in Batangas. So LISP3, sorry, LISP3, the first industrial township, first Philippine Industrial Park 2, and the LASP4. So they emerge as zones with substantial infrastructure that could benefit from transitioning to natural gas. So LASP3 here is heavily dominated by in-house generation and chillers. LASP4 and the first industrial township, they have more balanced facility types, which include steam boilers and burners. FPIP2, they have strong concentrations of generators, boilers, and chillers. And for the next slide, here we see the most common fuel for in-house generators is diesel, and some locators use biodiesel for the in-house generators. For the boilers, they either use diesel, biodiesel, or LPG as fuel. Furnaces are most commonly powered by LPG, and chillers are fueled by LPG, diesel, propane, biodiesel, or coal. For the next slide, The next slide is the power connection. So based on the survey, so all respondents noted that they use electricity for their operations, and 89% of them responded that a distribution utility or a DU supplies their electricity, while 11% of the locators mentioned that they get their power supply from a retail electricity supplier. None of them generate their own electricity, nor they connect to a power plant or to a microgrid. And here we just show that the flow of electricity from power generation to consumers follow physically the same path, and they just differ in the market they service, so the contestable and the captive markets. And for the this table shows the differences or the mix of DU and RES in the SEZs in Batangas. So we can see here that the AGNP, LASP4, and the Lima Technology Center are entirely powered by DU, while the FPIP2 operates solely under an RES, so 100% RES, while zones like the First Industrial Township and LISP3 and a little bit of, LISP3 has a mix of both DU and RES. For the first objective, the recommendation is so clustered SEZs such as LASP3 and 4, FPIP 1 and 2, and then FIT. They are already clustered in the Tanawan area, which is a good site for a regasification facility. The FIT, the First Industrial Township, and FPIP2, they have flexibility with the RES sourcing and significant consumption, and they could also be ideal pilot zones for embedded natural gas systems. For the second objective, which is on the logistical requirements for LNG, so as Batangas SEZ has been identified as the target market for the pilot usage of LNG in industrial zones, 2 import terminals nearby have been identified for potential natural gas supply. So the first one is the PH LNG terminal in Ilihan, Batangas, and the second one is the first gen LNG terminal in Santa Rita, Batangas. And we see here the locations of the 2 import terminals at the bottom, along with the SEZs and power plants. So the SEZs are mostly concentrated in the Tanawan area, while the power plants are down near the import terminals. So the corresponding, so we are looking at possible transportation routes, and we arbitrarily chose FPIP for the site for the regasification facility. So the corresponding transportation routes to the arbitrarily located FPIP are shown in this graph. And so the first one is from the PH LNG terminal to FPIP, so it covers roughly 75 kilometers. The second one, next slide. Yeah. So this one from the first gen LNG terminal to FPIP is approximately 53 kilometers, so passing through major roads and highways. And then in the next slide, we have the different modes of transportation for the LNG, which is the gas pipeline and the virtual pipeline, or what we know of lorries or trucks or ISO containers. So pipelines are ideal for steady, high volume delivery to cluster industrial zones. They are efficient, but they require high upfront cost, long construction time, and are fixed in place. So it limits the flexibility. Whereas the virtual pipelines or the lorries, the trucks, or ISO containers. So these are cryogenic ISO containers, and they are quick to deploy, lower in costs, and adaptable to changing demand and geography, which makes them a practical solution for distributing LNG to multiple areas in Batangas. And then for the next slide, we see here just the comparison between a compressed natural gas and liquefied natural gas. So as an alternative to traditional pipelines, virtual pipelines may carry compressed natural gas or the liquefied natural gas. Shown in this table are the differences between the two states. And in particular, LNG has to be kept at cryogenic conditions at all time when transported by truck. In the next slide, we see handling. So the handling of LNG, so from the truck to the regasification facility, we start with the loading by replacing or purging. This is necessary to replace the air with nitrogen when loading LNG to the vessel for the first time. And then it follows with the cooling down phase. The loading operation begins, and then transportation via the virtual pipelines. And when it reached the facility, so we have the unloading operation that will be received by the base station pump or by the base station pressurizing vaporizer. And for the next slide. So for the storage, we see here the three common types of LNG storage. These are the flat bottom tanks. So the single containment, the outer tank serves as an insulation and captures the vapor purge gas pressure, but then it cannot contain the liquid once it leaks. The double containment tank will contain it. The secondary container will hold potentially the leaks, while the full containment tank, both the inner and outer tanks hold the refrigerated liquids. So, but these are for large-scale LNG storage tanks. And in the next slides, we see more innovative storage through LNG, which are the bullet tanks. So these are modular prefabricated tanks. Given the limited land availability, so these bullet tanks offer a practical solution, and they are more space efficient than traditional flat bottom tanks. They are easier to install, and they allow for incremental expansion. And next slide, please. So the regulations for the transport, when transporting LNG, compliance with multiple regulatory bodies is essential to ensure the safety, the legalities, and operational efficiency. So we identified the DOE, LTFRB, LTO, and DPWH, but then a colleague from the DOE earlier also pointed out the participation of PNP in transport of LNG. Thank you very much for that. And for the recommendation for this particular objective, we recommend the use of virtual pipelines to transport LNG from the terminal to SEZs. This approach is more flexible and cost-effective. And storage and bullet tanks for storage of LNG. And finally, all systems should comply with DOE guidelines and also international guidelines such as that of NFPA 59A to ensure safe storage, handling, and transport of LNG. And the results for Objective 3 will be presented to you by Engineer Nalzaro.
Good afternoon, everyone. I am Sir Paul Jake Nalzaro, and I will be presenting the results of the Techno-Economic Assessment or analysis of the proposed LNG facility. So, starting from the import terminals, the imported LNG will be transported to this to the location of the proposed LNG facility via virtual pipeline or the trucks. At the facility, the LNG will be unloaded to the storage tanks under cryogenic conditions, and then it will be sent via pumps to the vaporizers for regasification for its usable natural gas form. Once it's in the natural gas form, the natural gas will be distributed to the different Batangas SEZs via conventional or embedded gas pipelines. From the recently conducted survey by our counterpart economics team, 500.99 mmSCF of energy consumption is projected for 2050, incorporating the 4.9% average change projected by DOE. This is equivalent to 3,680 cubic meters of LNG if we propose to address 100% of this energy consumption. This leads to a daily throughput of the proposed LNG facility of about 11 cubic meters, which is calculated with approximately 335 operating days per year. And this facility will be located in Tanawan, Batangas, most likely within the vicinity of the First Industrial Township or FIT and the First Philippine Industrial Park or FPIP, where majority of the energy-intensive equipment are present, so as mentioned by Ma'am Thea earlier. Next. Before. However, the capacity is still too small compared to industrial scales of current LNG facilities. To maximize financial returns, the engineering team, Ma'am Thea and I and our student assistants, propose a different scenario wherein a turnkey power generation is included in the proposed LNG facility to provide power to nearby power plants. And this is on top of servicing the natural gas. So for this pilot LNG facility, a 1 megawatt turnkey power generated requires about 17,000 kilograms per hour of LNG, which corresponds to a daily throughput of 30 cubic meters. So this is about 3 times the initial calculation of the daily throughput. So shown on the screen is the process flow diagram of the LNG facility, which we have generated through Aspen HYSYS. And we can divide this diagram into 4 sections. So the first part is the storage, followed by the recondensation or the recovery of the boil-off gas, which I've said earlier. So for those who weren't present here this morning, boil-off gas is the vapor that evaporates from the liquid form of LNG once it's being unloaded from the trucks to the storage tanks. Okay, and once the boil-off gas has been recovered, and including the LNG at the storage tanks, we then send them through pumps to the regasification unit or the regasification section, and the natural gas will be distributed to the different areas in Batangas. Starting with the storage section, the proposed facility is expected to process 30 cubic meters of LNG per day. Yet, still, this is a number too low compared to what commercial LNG storage tanks process. So for reference, commercial LNG tanks, LNG storage tanks service about hundreds of thousands of cubic meters of LNG. So you could just imagine how low of a number this 30 cubic meter is. No. So instead of proposing a full containment tank, which we proposed in GPDP 2 to 3 years ago, instead of using the full containment tank, vertical bullet tanks are said to be an option, particular for small-scale LNG facilities. This storage tank should be able to hold LNG enough for a few days. And should there be a need to increase the capacity of the serviceable LNG, rows of multiple vertical bullet tanks can be used. From the storage tank, two types of send-out pumps are usually present in the LNG facilities. So these two are the low pressure or the LP pumps and the high pressure or the HP pump. The LP send-out pump supplies flow to the recondenser and feeds the HP pump. Meanwhile, the HP send-out pump takes suction from the BOG recondenser and pressurizes that to meet the send-out pressure requirements. Please. Okay, thank you. The facility will also include a boil-off gas recondenser system to recover the natural gas and to prevent risk in physical damage of the sudden expansion. So, starting from the liquefied form, for context, if we have a liquid form of a certain substance, tas bigla siyang nag-vaporize, nag-expand kasi siya. So, it can cause, it has high risks, hazard, and then it can also potentially cause material failure pag sobrang biglang lumaki yung volume. So the main unit may be designed with packed section where vapor and liquid phases contact for heat exchange as shown in this diagram. However, in our simulation, no BOG was generated, and this could be explained by the fact that the current service capacity of the proposed facility is too small to generate a significant amount of boil-off gas. Nevertheless, we still included a BOG recondensation system as a backup should there be any BOG that will be recovered, and the backup compressor outlined in yellow in the simulation image of the process flow diagram we showed earlier compresses any boil-off gas from 100 to 1,000 kilopascals. Vaporizers in the regasification section convert the LNG back to natural gas before it is distributed to the different SEZs. So there are three common types of vaporizers depending on layout and utilities used. So the first one is the open rack vaporizer or the ORV. Then we also have the submerged combustion vaporizer or the STV, and the ambient air vaporizer or the AAV. Among these three, on the global perspective, the most common is the ORV. However, ORV is not an option for this particular case since there are no bodies of water near the SEZs. Meron malapit sa import terminals but hindi sa SEZs. Tama? And between the remaining two, between the SCV and the AAV, the latter, which is the AAV, is a better option for less cost on heating media. In particular, we will only be needing to use the ambient air as our heating utilities. Kasi sa Philippines, humid yung air natin compared to other locations in the world. Adopted in the simulation is the direct expansion cycle, wherein two AAVs are connected in series. So for example, we have AAV1 and AAV2. And an intermediate turbine is also included for the proposed turnkey power generation of 1 megawatt. Other power cycles, such as combined direct expansion and Rankine cycle, and combined direct expansion and cascaded Rankine cycle, have been gaining traction, but the engineering team did not consider those as these are more complex and require in-depth technical background of energy consumption. We might be able to consider those in the future, but for now, for this benchmark case analysis, we'll consider the simplest one, which is the direct expansion cycle. The last section of this chemical process synthesis is the distribution section. The natural gas product will be distributed to the various SEZs dispersed throughout in Batangas via gas pipelines. So since we're talking about kilometers of gas pipelines, our natural gas would have to be discharged at really high pressures. So high discharge pressures are needed for these natural gas to be delivered to different locations. And one common way to cope with the need for the high pressure generation is a multi-stage compression, where multiple compressors are used and discharge pressures are staggered. So for easier explanation, if we were to use a single compressor, we would have to compress the natural gas from, hypothetically speaking, 1 kilopascal to 1,000 kilopascal. So sobrang taas ng pressure change na yon, and that would lead to material failure because the high pressure would also yield high temperatures. So if we're talking about metal equipment, pag tumataas yung temperature natin, nagkakaroon tayo ng material failure. So to address this possible risk, we're suggesting the multi-stage compression, and in between the compressors are interstage coolers to reduce the temperature before we send them back to another compressor unit. So the proposed LNG facility utilizes a two-stage compression, and both compressors were set to have a pressure ratio of about 8.6. So our team did a sort of an optimization study. So we explored the use of 3-stage compressors and 4-stage compressors. However, there is not much change in the operational costs when we checked the 3-stage and 4-stage compressors. So we opted with the 2-stage compressor kasi mas napapamura tayo sa capital costs. Okay? So that's for the technical part of this proposed LNG facility. Moving to the financial analysis, our financial model assumes a WACC, or the weighted average cost of capital, of 8.1% based on sector norms. We assumed demand would grow annually by 4.9% and tested 2 demand scenarios to estimate the financial viability. The key assumptions made in this economic analysis are detailed in this table, particularly for the values or the costs entailed that we use in our computations. Moreover, the capital and operating cost estimates, including the utilities, were obtained from the economic process analyzer from Aspen HISIS. The rest are estimations using percentages of capex and total product costs as outlined by our main reference from the Peter and Timmer House. So as mentioned earlier, we'll be exploring 2 different scenarios. This financial analysis explores the economic feasibility of distributing regasified natural gas across SEZs in Batangas. So the first scenario considers the distribution of natural gas solely for non-power applications. And the second one expands this framework to include both thermal applications and embedded 1 megawatt turnkey power generation, enabling natural gas to serve as a dual-purpose energy source within the SEZs. Next, please. Starting with the first scenario. So this scenario focuses solely on the use of LNG for industrial heating and cooling processes with a consumption of 511,000 MMBTU for year 1 and constantly increasing by 4.9% through the end of the facility's useful life, which we set to be 20 years. The initial year revenue from gas sales yields $6.5 million. The total year 1 expenditure amounts to approximately $19 million. Sadly, however, for year 1, for the first scenario, the resulting cash flow or the net present value is negative, primarily due to the low demand for gas and high regasification costs, which led us to the second scenario. So the second scenario expands LNG use to include the embedded power generation. And for this scenario, 1 megawatt of turnkey natural gas power generation is added. The initial revenue from gas sales and power generation totals $40 million. Given this result, scenario 2 yields a strong financial performance and robust returns with an NPV of about $42 million and a high internal rate of return of 19%. This affirms the feasibility of integrating heating, cooling, and power applications into a single LNG hub. As for the last part of our financial analysis, a sensitivity analysis was conducted to determine the effect of changes in different variables. So, looking at the scenario 1, sensitive analysis for scenario 1, variations in the LNG purchase price and natural gas selling price showed minimal impact on the NPV, primarily due to the narrow profit margin between the benchmarked selling price of $12.8 per MMBTU and the assumed LNG purchase cost of $11 MMBTU. So ang difference na po natin ay less than $2 per MMBTU. A wider price differential would improve profitability and increase the likelihood of a positive NPV. Another key limiting factor is the low natural gas demand in Batangas SEZs, which we've highlighted for multiple times already. For further visualization, to get a break-even of this scenario 1, the facility must sell at least 1.4 million MMBTU annually. This is nearly thrice the originally predicted projection, the original projection, which is 500,000 MMBTU. In scenario 2, changes in electricity prices have a stronger influence on returns. So for example, looking at this row, a 10% decrease in electricity price reduces the IRR to 9%, while a 10% increase pushes it up to 28%. The model results in a negative NPV and IRR when the market share of power generation is reduced by 10%. Overall, scenario 2 exhibits strong financial potential withstanding moderate shifts in key variables, including the assumptions that we set arbitrarily earlier. So, as a conclusion to our techno-economic feasibility, the proposed small-scale LNG storage and regasification facility in Tanawan, Batangas is technically feasible and strategically located near SEZs. It is suggested to prioritize integrated systems like that in scenario 2, combining heating, cooling, and power to maximize LNG utility to improve financial outcomes. As for the recommendations and ways forward, regulatory support for embedded networks can also help shape implementation. Embedded networks or localized systems that distribute electricity or thermal energy within a defined area, such as industrial parks or special economic zones, may face regulatory ambiguity where franchise areas are strictly delineated. So I guess that's all from the engineering team. Thank you for your attention and have a good day.
Now we open the floor for our questions. Anyone from our audience on site?
I noted that there is a mismatch between in the uptake of RES versus regular DU supplier. I wonder why that is the case. Is it because price differential is not attractive enough? Or if there are certain rules such that certain locators is not able to or are not qualified to become RES buyers of electricity.
Actually, we don't really have the answer to that because it was not part of the survey when we conducted that. But I guess from the questions that we asked in the survey, like for example the consumption, so many of them will not qualify. Yeah, yes, they're too small for RES. So only like we see here. Yeah. Yeah, so like for example, we only see here for FPIP, it's only 20%. 20% of the locators get their supply from RES, or even LISP3, it's only 6%. So most of them are like office-based, or they have very small consumption that will not qualify them for RES.
Is that because the floor, the volume is too high? In other words, kung 500 ka, kung 500 ang floor mo, people below ka na.
Yeah, Yeah, I think they have specific threshold for you to qualify for RES.
Ano ba ang threshold ngayon? 500 pa rin o 250 na?
750 po yata.
750?
Yeah.
So hindi pa bumaba to... Hindi pa bumaba.
500.
500.
Yeah, but I think I don't know, maybe the uptake of locators in that area, yeah, medyo
Associated
mabagal.
with
Yeah.
ano, with the that's really a DOE rule as to how much you buy before you qualify.
Yeah.
So maybe if it is lowered, more people will
Qualified
Will qualify.
for the RES.
and some of the calculations will change simply because it will be cheaper to
Yeah, and they have more
maintain.
flexibility with RES.
All right. Thank you, Professor Fabella, for the question. Okay. Kindly state your name and your affiliation, ma'am, before your question. Thank you.
Hi, good afternoon. So I'm Krista Rayos del Sol from Accelerate Energy, Luzon LNG. Just looking at the financial analysis, I noticed the delivery via virtual pipeline is at 250 per MMBTU. I'm just wondering if this is a direct reference from Pratson, or did you investigate delivering the LNG from the terminal towards, let's say, the hub? And when you did that, or if you consider that, did you just do the smaller? Because I know ISO tanks have two sizes. You could do a 20 cubic meter, or a 20 footer or a 40 footer. Did you just do 20 footers, 40 footers, or were those ever considered in the logistics? Yeah, that's about it.
Yeah,
Thanks.
so yeah, thank you for that question. So it's just a benchmark 20 footer ISO container. So benchmark from the one that they're using in the US, and then translating it to the Philippine context. So the kilometers, so medyo inano lang namin. Binase lang namin the kilometers wise in the US, and the travel distance also here in the Philippines from the import terminal to the SEZ.
Thank you very much for sharing that, because we've also, as a business, tried to look at it. And I just want to share that I understand that when you do that, some of the factors, because it's a logistics game when it comes to virtual pipeline delivering from one hub to another. I think for our regulation, for LNG ISO tanks or even CNG, we are limited to the 20 footer. As opposed, if you were to economically make it more feasible, it's for 40 footer is always modeled for the US, I think. And then, so there's sort of a gap from that reference to this application.
Yeah,
I
it's
think.
it's actually just the 20. So we're looking at the lower
20,
scale,
20,
yeah, the lower scale, especially for the demand in Batangas, which is really low.
50, yeah.
Yeah.
Thank you.
Thank you.
Thank you, Ms. Krista. How about our Zoom participants? Hello there, everyone. Gising pa ba lahat? Please react so we can see you. Okay, so mukhang tahimik silang lahat. So now that kung wala nang questions from our participants on site, if there's none, we've earned a break, coffee break, all right? Para magising naman tayong lahat. So now, thank you again. Let's give a warm of applause to Engineer Paul Nalzaro and Ms. Thea Baltazar.